All right, let's take a quick look at the calendar. So we are, let's see, so we're right here on the 29th, February 29th. Doesn't happen very often. Let's see, so we're going to cover 5.4. We're going to get through most of it today. You can get started on the homework assignment. We'll finish it up tomorrow. We've got a review. The review is already posted online, so I would download that and I would get started on that at least by tomorrow so that you come Friday with questions. Because when you come back on Monday, that's the exam. You're going to turn in the review. You're going to turn in 5.4, and you'll just take the exam, and that's it. Okay? We've got a full week next week, and then the following week is full, and then we'll finish by covering 6.3. This day is going to be pretty easy. This is the last day of the term, so the third quarter ends right there. So you can't do anything to change your grade after that. Okay? Any questions? All right, let's take a look here. Okay, so this section is on complex zeros of a polynomial, and the first one is called the fundamental theorem of algebra. Okay, polynomials are really important. They're kind of fundamental to everything that we do in algebra. Somehow we try and work our way back to those no matter what we're doing. It says every complex polynomial f of x of degree n greater than or equal to 1. So if it's degree 1 or more, it has at least one complex zero. At least one complex zero. Okay? So all this says, this is, I mean, it's not that ugly, but it's not the greatest. In other words, we're guaranteed at least one. We're guaranteed at least one zero. So we're not going to sit there and spin our wheels for an hour and say, hey, you know what? This doesn't have any answers. There are no zeros. There are no x-intercepts. There are no solutions. Okay, we're going to find at least one complex zero. Guaranteed. Okay? Okay, this next one is kind of ugly. It says every complex polynomial of degree n greater than 1 can be factored into n linear factors, not necessarily distinct, so that means there could be some repeats. We've actually seen that before. It says you can make it look like this, so you can pull whatever constant you need out front, okay? Where those are all complex numbers. So the number out in front and every single one of those roots or every single one of those zeros is a complex number. Okay, so it says that is every complex polynomial of degree n greater than or equal to 1 has exactly n complex zeros, some of which may repeat. Okay? All right, so in other words, we're guaranteed that every polynomial can be factored. You can factor the whole thing. And if it's degree 8, we're going to have 8 zeros. If it's degree 7, how many zeros are we going to find? 7. If it's degree 2, we're going to find the 2 of them. Okay? All right, the next one is the conjugate pairs theorem. And it says if we've got a polynomial whose coefficients are real numbers, if a plus bi is a 0, then a minus bi has to be a 0 also. Okay? So this says imaginary zeros always come in conjugate pairs. So let's write down an example. Let's say 3 plus 2i is 1, 0. What's another 0? 3 minus 2i. Okay? Okay, everybody watch carefully. Let's say negative 4i is a 0. What else would have to be a 0? 4i. Okay? It's just the imaginary part that changes sign. The real part stays the same. Okay? So on this one, this would be 0 minus 4i and 0 plus 4i. Okay? Yeah. Sure.
Could negative 4i also be written as 4i squared? Or 4i cubed?
Yeah, I suppose you would, but we'd always simplify something like that. Okay? Good thinking. That won't come up very often, but you are correct. Okay? In fact, I've never seen it come up. But you are correct that you could write it that way. Okay, the next one is a corollary. This is just kind of a related idea. It says a polynomial f of odd degree with real coefficients has at least one real 0. So what that means is it has to cross the x-axis. Okay, so if it's an odd degree polynomial, remember what those look like. Okay, they either start down here and end up here, or start up here and end down here. There's no way you can go from the negatives to the positives without crossing through 0 at least once, okay? So if the polynomial is of odd degree, we're guaranteed at least one real 0, which means there's at least one x-intercept, right? And we could, I've explained it, we could draw a picture why. If it's of odd degree, it's got to start down here and end up here, so it would have to cross through there once. If it had a negative coefficient, it would have to start down here, or excuse me, start up there and end down there. It would have to cross at least once, okay? And then the last theorem, and then we'll put these into practice. It says every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of linear factors and irreducible quadratics. We actually talked about this one before. So in other words, let's see, if we use, so I've got a typo there, if we use only real numbers, then we're guaranteed that we can factor the polynomial into linear factors and or irreducible quadratics. So let me blow this up so we can take a look at these. Here are some linear factors. We like those. Those are the ones that we're used to dealing with. Those come up quite a bit. We know what to do with each one of those. We know what the zeros are that come from those. Okay, each one of these is an irreducible quadratic. Okay, it doesn't factor. Okay, and in order to solve this, we're going to have to use either the quadratic formula or, let's say we take this one right here. How could I find the two answers that come from this? Yeah, they are going to be imaginary. I could set this equal to 0. Whoops, that's a plus. So this would be x squared equals -9. Take the square root, so I get x equals plus or minus 3i. So notice I got one that's 3i and its conjugate -3i. Okay? So those are linear factors and those are irreducible quadratics. Okay, you can solve, if it's a really easy irreducible quadratic like this, you're in great shape. You can just take the square root, move it over, take the square root. If not, what would you use? What could you always use to solve an irreducible quadratic? Quadratic formula, which is like what we talked about the other day. Okay, are there any questions? Okay, let's flip the page over and let's do some of these problems. So the cool part about this is if you've been paying attention in 5.1, 5.2, and 5.3, and especially with that little review day that we had yesterday, I've actually shown you nearly everything we need in order to solve the problems in 5.4. All it is rather than in 5.2 where we said, hey, find all the real answers, and maybe we got to a point where it was a degree 4 polynomial and we found 2 of them are real and then the other ones were imaginary and we ignored those for the time being. Now we're going to find all of them. Okay? So if it says find the real ones, you only find the ones without i's. If it says find all the complex ones, that means find all of them. Find them whether they have i's or nots. So this one says find all the zeros of that function. Find every single one of them. Which ones would we like to find first?
The nice ones.
The nice ones. And when we find the nice ones, how do we find the nice ones? P and Q. So let's start with P and Q. So P is 6, Q is 1. That's good news here because we're pretty good at this point, right? We can just write down plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. There's my list of possible rational zeros. Now, let's keep in mind the theorems that we've been talking about. What degree is this? Degree 3. How many zeros are we going to find? We're going to find, okay, there are up to 3 real zeros, but we're guaranteed, based on those theorems that we talked about today, we're guaranteed that there are 3 complex zeros. Some of them might be imaginary, but there are 3 answers, no doubt about it. We're going to find all 3 of them, okay? Especially given the fact that the instructions say find all of them, okay? Doesn't matter whether they're complex or imaginary or real or whatever it happens to be, okay? So let's check and see. Let's plug in a 1. That would be a 1, that would be a minus 2, that would be a minus 5, and that would be a 6. What does that make? That makes a 0, okay? So, without even doing much work, we know what one of them is, but I'm going to find the rest of it because we need that depressed polynomial. So we're going to put it in synthetic division here. 1, -2, -5, and 6. Bring down multiply, add. Multiply, add, multiply, add, so we get 0. So again, what does that mean about this number right there? That number is a 0. That means it corresponds to a factor. The factor happens to be x minus 1. What do I write here? The depressed polynomial. Go ahead and write it down. X squared minus x minus 6. Okay, this is a quadratic. Is it irreducible, or could we factor this? We can go ahead and factor this. So we're looking for two numbers that multiply to be -6 that combine to be -1. So that's going to be -3 and +2. So here are all the factors. What they wanted were the zeros. So the 0 from here is 1, the 0 from here is 3, and the 0 from here is -2. Okay, that's pretty easy, right? Okay. Nope. These are all the factors. These are all the zeros. There are 3 of them, and they all happen to be real numbers. So this problem could have easily been in section 5.2. Right? Okay, let's try another one. Any questions there? Sure we're ready to go on? Okay, all right, let's take a look at the next one then. It says find all the zeros. Okay, this one looks a little bit worse. It's degree 3, so we're going to find, we're going to find all 3 zeros. No matter what it takes, we're going to find all 3 of them. So we want to find the nice ones first, so let's do the P and Q stuff. P is 3, Q is 2. Okay, so this isn't as nice. We've got 1 and 3 and 1 and 2, so I've got 1, 3, 1/2, and 3/2, plus or minus in front of each one of those. Now, we're not saying those are the answers. We're just saying, look, if I've got to find 3 answers, I want to find the nice ones first. I want to find the rational ones first. Okay? So here's my list of possibilities. 1 and -1 are pretty easy to check just by looking at it. If I plug in a 1, I get a 2, a -1, a 2, and a -3. Well, 2 and 2 make 4, and -1 and -3 make -4. So if I plug in a 1, what do I get? I get a 0. Now, that without writing anything down, we know one of the zeros, but that doesn't help me find the other 2 until I factored it. Okay? And I do that using synthetic division. So again, we'll put 1 in the box. We're going to put a 2. Again, please make sure you're careful with this. Equally space things out. Make sure you haven't skipped any powers. You keep the signs correct and all that sort of stuff. Okay? So we're going to bring down, multiply, and add. So this is going to be a +1. We're going to multiply. That's a 1. This is going to be a 3. And then we're going to multiply. That's a 3. So that's a 0. So we're in good shape there. So that means, again, this one right here is a 0. We already knew that. We've got one of our answers. That means the factor that it corresponds to is x minus 1, and then we write down the depressed polynomial. So this is going to be 2x squared plus x plus 3. Now, okay, can somebody remind us, why do we call it a depressed polynomial again? Because we lowered the power. Okay, it used to be degree 3, now it's only degree 2. What do we like about depressed polynomials? They're easier to deal with. That's the bottom line. Okay? Now, sometimes we'll get something that's really easy to factor, sometimes not, but at the very least, it's a lower degree. Now, this one here, and the last 2 examples, in fact, this one happens to be a quadratic. Let's see if we can factor it. Again, you can check to see whether this factors. Multiply the 2 and the 3 together. That's a 6. Are there any numbers that multiply to be +6 that combine to be +1? No. This is an irreducible quadratic. So to get the 2 answers that come from this one, what do we have to do? We have to use the quadratic formula. So we're going to do x equals -1 plus or minus 1 squared, so that's going to be a 1, and then minus 4 times a times c, so that's a 2 and that's a 3, all over 2 times 2, so that's a 4. Take a look at that. I said that really quickly. Is everybody good there? Easy enough? The part, again, we have to be careful with is this right here. This is going to be a 1, and it's going to be a minus 24. It's 24, right? Okay. So what we get is negative 1 plus or minus square root of negative 23 over 4. So that's fine, but we really ought to simplify that negative there. So this is negative 1 plus or minus I radical 23. 23 is a prime number, so we don't have to worry about that. Okay? So one of the answers was 1. Another answer is negative 1/4 plus I radical 23 over 4. And the other one is, well, wait just a second. Everybody listen. If we know this is one of the zeros, and it's an imaginary number, don't they always come in pairs? So we don't even need to look at this anymore. I can just say, well, this one's going to be negative 1/4, and instead of a plus, it's going to be a minus I radical 23 over 4, and there are the 3 answers. Okay? 1, 2, 3. Now, it was degree 3. We're guaranteed 3 complex zeros. We found all 3 of them. Remember, we're also guaranteed if it's an odd degree polynomial, one of them has to be real. Is one of them real in this problem?
Yes.
Yes, it is. Okay? All right. Any questions? Okay. You don't have to write down the factors, so don't write this down. If they did ask you to write down the factors, this is what we'd write down. We'd write down x minus 1, and then we'd write down x minus this stuff right here. So that would be a plus 1/4 minus I radical 23 over 4, and then x plus 1/4, and then it would be plus I radical 23 over 4. Those are really nasty looking. The other thing you need to keep in mind is if we multiplied these x's together, that would just make an x squared. An x cubed. It started off with a 2. So remember in those theorems it said there could be a number out in front. Okay, in this case it would probably be a 2. Okay, you don't have to do that on this one. Okay, so I just want you to just be aware of how that works. Okay, are there any questions there? Okay, let's take a look at the next one. It says a polynomial of degree 5 with real coefficients has zeros 1 plus I, 5i, and 1. Use the conjugate pairs theorem to find the remaining 2 zeros. So, it's degree 5. How many zeros do there have to be? There've got to be 5. They gave us 1, 2, 3. How many more are there? There are 2 more. How can we find them? They always come in conjugate pairs. So if 1 plus I is a 0, what else has to be a 0? 1 minus I. So there's another one. And if 5i is a 0, what else has to be a 0? Yeah. Okay, so here is 1, 2, 3, 4, 5. There are all 5 of them. You have some problems that are literally that simple. Okay. Any questions? Okay, let's take a look at the next one then. It says find a degree 4 polynomial. How many answers should there be? There should be 4. Okay. With real coefficients that has zeros, let's see. Negative 4 plus I and 1 with multiplicity 2. So there's 1, but its multiplicity is 2, so there are 2 of them like that. And here's the third one. And if negative 4 plus I is a 0, what else is a 0? Negative 4 minus I. Okay, now, is that the answer to the problem, though? Okay, it's not. Okay, it's not the answer to the problem because it says find a degree 4 polynomial. So here's what we're going to do. We're going to write down there's a 0, negative 4 minus I is a 0, and negative 4 plus I is a 0. Those are all the zeros. Let's write down the factors. So the factor from this one would be x minus 1. The factor from the next one would be x minus 1. Can you see why they said multiplicity 2? because you could write that as x minus 1 quantity squared. And then this one is x, help me out here. Okay, it's going to be x minus all of this stuff. So that's going to be plus 4 plus I. And this one's going to be x plus 4 minus I. See how that works? Okay, there are the factors. Any questions? Okay, so we got the factors taken care of, but we don't have the polynomial yet, so what we have to do is we have to multiply these together. Okay, now that can be a fairly long process, especially if in 1010 you didn't take the time to memorize those perfect trinomial square patterns and stuff like that. Okay, let me show you, so I'll show you this two ways. So we could just go through and we could multiply here and here, here and here. That's going to give me x squared minus x plus 1. Collect the like terms, so that's going to be x squared minus 2x plus 1. I could go through here, watch really carefully here. I've got to take the x and multiply it by that, that, and that. Then I've got to take the 4 and multiply it by that, that, and that. Okay, what do I have to do last on this one? Take the I times x, I times 4, and I times negative I. Okay, I can go through and I can do that. I'll get 3 terms here times 3 terms here. I'll have 9 terms. And I've got to collect all 9 of those terms. So here's what we get when we do that. We get x squared plus 4x minus xi. Then we get 4x, 16, and minus 4i. And then I get plus xi, I get plus 4i, and I get minus I squared. So there are all 9 of the terms. That's a bit of a pain in the butt, isn't it? Okay. Take a good look at it, though. Here's a minus xi, there's a plus xi. Those go away. Here's a minus 4i and a positive 4i. Those go away. So what I've got here is I've got x squared, I've got 8x, and then I've got 16. And what does negative I squared count as? Counts as a positive 1. So this would be plus 17. Okay? Everybody with me? Okay, do you want me to? Okay. So to finish this off, then you have to multiply here, 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 here. And that's a lot of multiplying, isn't it? Okay. Should we make it a little bit easier? Okay, watch. Okay, it's x minus 1 quantity squared, and it's x plus 4 plus I, and x plus 4 minus I. You with me? Okay, there's no getting around this one right here. Okay, this one, you either need to multiply it out or you need to know that pattern for a perfect trinomial square. So that's going to be x squared minus 2x plus 1. Okay, that one should be something that you're able to do quickly from Math 1010. Watch, please. X plus 4 plus I, x plus 4 minus I. Let me say that again. X plus 4 plus I, x plus 4 minus I. Does that pattern sound familiar at all? It's kind of like x plus 2, x minus 2. That's a difference of squares. They're conjugates, right? So I should be able to just take a perfect square of the first one. So that's going to be x squared plus 8x plus 16. And then minus a perfect square of the second one. The second one is I. So when you square I, you get negative 1. What's a minus minus 1? Plus 1. So this is x squared minus 2x plus 1, x squared plus 8x plus 17, and then take a look here. Isn't that what we got over here? Okay, but quite a bit quicker. So you can use the conjugates, the difference of squares, those patterns for difference of squares, perfect trinomial squares and stuff like that. You're still stuck multiplying the two of these together, but at least we got to here much quicker than we did before. Okay? Any questions? By the way, if you multiply these together, what's the first term going to be? X to the 4th. And didn't they want a degree 4 polynomial? Won't that work out the way it's supposed to? Okay. Any questions there? Okay, good. Next page. Go ahead and flip that over. Okay. So this one says, find the complex zeros of the polynomial function, then write the function in factored form. What degree is this? Degree 4. How many zeros do we need to find? We need to find 4. And because it says find the complex zeros, that means find all of them. Every one of them, whether they're real, imaginary, or whatever. Okay, so we're going to find all 4 of them. Okay, now take a good look at this. This probably is the most difficult one we've done so far. Notice that it has 5 terms. Do you know how to factor 5 terms? Nope. Me neither, other than the way that I'm going to show you right now. Notice that we can't even take out anything common to all of them. There's a 3 here, here, and here, but there's a 5 in those. There are no 3s. Okay? So if we have to get this done, I mean, pretend it was like this. I give you a couple hours and I give you $200 if you can solve this. I don't have that, believe me. Okay? But if you had that much time and you were given enough of an incentive, could you factor this? Could you find all the zeros? Sure. Which ones would we want to find first? The nice ones. So we'd start with P and Q. So we're going to start with P and Q. That's 18, and that's a 3. Now these are not the nicest P's and Q's because look at 18. 1, and 2, and 3, and 6, and 9, and 18. Holy cow, a list of 6 factors right there. And for 3, it's 1 and 3. Okay, is everybody watching? Okay. If I do each one of these over 1, I'm going to get this list again, right? So I'm going to leave that list alone, and then I'm just going to add 1 over 3, 2 over 3, 3 over 3 is 1, don't need to write it again. 6 over 3 is 2, don't need to write it again. 9 over 3 is 3, don't need to write it again, and 18 over 3 is 6, don't need to write it again. So here is my list. See how that saves a little bit of time and a little bit of space rewriting and all that sort of stuff? So we put plus or minus in front of all those. How many possible rational zeros do we have on that list? 16. Is there any way they could all work? No. This is just a list of possibilities. These might work. Hopefully we get a couple that do. Okay, but if there are any nice ones, they have to come from that list. Okay? What do you want to check first? Okay, I heard a 1, and then Emily said -1. Emily, why do you say -1?
Because there's so many positives up there.
Okay, that's fabulous. If you've tuned out, I realize this is not the most thrilling thing on the planet. Okay? I'm a professional mathematician, and sometimes this gets a little old. All right? Okay, so wake up, pay attention. The value here is not that anybody's going to ask you, other than in 1050, how to do a problem like this, but you are going to use your brains. Okay, now Emily just used her head. Okay, would you say that again? She doesn't even want to check 1, and here's why. Say that again.
Because there's only 1 minus 18.
If you plug a 1 in here, we're going to be adding 3 and 5 and 25 and 45. We're going to have this gigantic positive number, and the only thing to balance that out to get it back down to 0 is an 18. Is that going to work? We don't even need to bother with 1. Okay? We don't have to write anything down. We're just using our noodles. Okay? Got it? Okay. Should we try -1?
Yes.
Absolutely, because if we put a negative in here, some of these are going to turn negative. Okay, now rather than, once they get this long, I'd rather just do it using synthetic division. Okay? So I'm going to put -1 in the box, and I'm going to write down a 3, a 5, a 25, a 45, and a -18. You've got to make sure that you keep the numbers straight, keep them nice, neat, and organized. Okay? So this is bring down, multiply, add. Multiply, add. So this is going to be a 23. That's going to be a negative 23. Put those together. Let's see, 23, 25. So that's going to be, is that a positive 22? Okay. Do we make any mistakes? Does that one work? Nope. Okay. You can get rid of 1 and negative 1. Should we try positive 2? For the same reason. That's just going to make this a gigantic positive number, and we're going to subtract 18. That's not going to work for us. Should we try negative 2? Let's try negative 2. Let's see what happens here. So this is going to be a 3, negative 6, negative 1. That's a 2. That's a 27. Multiply here. That's going to be a 54. Negative 54, sorry. Negative 54, so that's going to be a negative 9. If I multiply here, that's going to be an 18, and that looks great. What does that mean about 2? That means it's a 0. So x plus 2 is a factor, and what's this stuff right here? 3x cubed minus x squared plus 27x minus 9. Okay, now, just pause right there. Just if you're working ahead, that's fabulous. I'm proud of you and everything, but I want you to think for just a second. Okay? We've only written down this much work, but we did a lot of mental work. We eliminated 1 and 2 just by thinking about how big these numbers were and how positive they were. Okay? So we've already got one of the answers, and look at our depressed polynomial. Okay, I'm going to blow this up just a little bit. Take a good look at that. We already know the answer that comes from here. Let's take a look at this. How many terms does that have? 4. Have we factored 4-term polynomials before? Yes, we have. Okay? So if we can rely on some of the easier tools, the simpler tools that we've learned in this class or in 1010, at that point, let's go ahead and use them. So let's take a look at this. Can I take anything out of there? I can take out an x squared. Okay, now I'm going to ask you the question on the next group, okay, because there's a 3x minus 1 here. Okay, I'm going to ask you what can come out of here, and I want you to say it the right way. Okay, I've said this numerous times. People make this mistake. Sometimes it hurts them, sometimes it doesn't. What can you take out of these? Positive 9. Thank you. Positive 9. We're left with a 3x and a minus 1. So take a good look here. I can take out the 3x minus 1, and I'm left with x squared plus 9. I'm going to still keep track of this guy right here. I know what comes from this one. I know what comes from this one. How many more answers do I need to find here? I need to find 2 more. This has a fancy name. What did we call this again? It's an irreducible quadratic. That means it doesn't factor using real numbers. It doesn't factor using real numbers. But it's a pretty easy one to solve. In fact, I think we've solved this one before. We just say, well, x squared plus 9's got to equal 0. X squared equals negative 9. Take the square root, so x equals plus or minus 3i. So this does factor over the complex numbers. This would be x plus 2, 3x minus 1, and this one would be x minus 3i and x plus 3i. Okay, these are the factors. Each one of those corresponds to a complex 0. What's the complex 0 that comes from here? Negative 2 from here, 1/3 from here, 3i, and from here, negative 3i. Okay, so here are the 4 zeros. How many zeros did we say we had to find? Needed to find 4, and we got it factored. Okay? So we found all 4 of the complex zeros, and we factored it. Okay, are there any questions? Okay, now take a look at that. That's a perfectly good test question. It's not too easy. Okay, this one, that's too easy. Okay, that's too easy for section 5.4. That one's not too easy, but it's not too hard, is it? I mean, we find one of them. Yeah, we had to go through 1 and -1 and 2 and that sort of thing. We had to sift through those. Okay, but once we got to here, we got something that we could use some other tools on that made it a little bit easier. Now, let's say you got stuck right here and you couldn't figure this out. You couldn't factor it. Couldn't you do the P and Q stuff again and just work on this one? You could. Your list is going to be a little shorter. It's not going to have 18 in it. Okay, but it is going to have the other ones, and you could just start that again. Okay, one thing that messes people up is they think, hey, you know what? -2 already worked. I can't use a -2 again. Is that true? No, because it could have a multiplicity of 2 or 3 or whatever. Okay, any questions? Okay. All right. Let's see. Can you do number 3? Number 4? Number 11? That's that pain in the butt where you have to come up with the factors and then multiply them all together. But you could do it, right? Okay. It's like the one that we did up above. Okay, tell you what. I'm going to let you go early today. Okay. I want you to review your notes, and I want you to get started on the assignment. Come tomorrow, we'll finish up 5.4. Please download the review so that you can be working on that over the next couple days. Today is Wednesday. The review is Friday. If you walk into class on Friday and you haven't even looked at the review, you're missing an opportunity to ask questions on stuff that you don't understand. Okay? Test is Monday. Okay. All right. Have a great day.